Hello, this topic is image stitching and the panoramic view. This is a coverage of chapter 9 titled Image Stitching of Zelsky's book. And a lot of those concepts are already covered in previous chapters, including the feature detection and what we talked about, the transformation, projection, that kind of a subject we already covered. Anyway, maybe for some of you that the word stitching seems to be new, and the panorama, I'm sure you know the words. So let me explain that what is stitching. Actually, unless you are a lady, then you may not know this, but using needle that you just use this colored thread, the string, and they're making some kind of a decoration or shape on a piece of paper, or just piecing many more than one sheets together just by needlework. So needlework to add shape by thread or other cloth. So there's threading, there's a threading by the needle or the other cloth is together. And the piecing together multiple objects or scene, that is what the stitching is. So stitch is more like the needle pricking, but nevertheless they're using those sharp objects. They combine multiple objects into one piece. So unite together by needlework or staple, and then mosaic is sometimes the word that is used in relation or related words. That is a picture made of pieces of images. So the old cathedral or building has this so-called mosaic. That is this different shaped pieces of the glasses with a different color. You piece those things together. So this is one piece, this is one piece, this is one piece. Different pieces. Those different pieces are all merged together to show or to form a very nice picture, just like that. Or in here, that what we are interested in, especially for the panoramic. Panorama is a pan is a wide, and the panoramic is a wide view. That's the kind of idea. So here's the three pieces of a picture taken in different angles. So one here slightly to your right, and another one, and slightly to the right, and the another one. So for example, those pieces and those pieces are same. It's overlapping, and then you obviously see those shape and the shape are same thing in two different. So you don't want show this piece of the scene twice. So rather move this picture and overlap here and get into glue together without showing any kind of a line or any kind of the discontinuity. So in doing so, another dilemma, of course, is that this one we see, in a sense, that very easily we see that this is a little farther away, smaller that is, and this is a little bit the bigger, closer, and this one goes smaller again. So that size difference is also a kind of challenge to make the picture smooth. So well done properly, then it looks like one piece of a picture that without any connection or any kind of there's a connection point that's called the seam. Seam is much like those trace of those glue. There's nothing. There's no sign of anything got glued together and one nice smooth piece. That is what we are talking about stitching. So in fact, that we are talking about the image stitching being multiple images, the pieces together into one larger one with a wider range of scenery. So this is very useful, and as a matter of fact, that this is the very standard form of features these days. A lot of digital camera, even if it's not very expensive, they have this panoramic option. So you take many pictures. Somehow then later on you come up with one nice picture. So the algorithm we are talking about today is actually all programmed in there. Okay, so let's see. So the image stitching wise, that just like what I have explained, that we have here 6 pieces of a sequence of pictures. So from left to the right. So this is one campus or some I don't know what it is, but it's some the dormitory and some building here. So in here, leftmost and the another one. This one seems to be somebody sitting, or it's a statue, I don't know. But these two are identical. This thing and this thing is the same thing. So we don't want showing twice, but this one somehow combined into one very smoothly. And then this piece is same as this piece. And then we got those. Then of course we see this one overlapped. So this one was taken in very quick succession with a lot of overlaps. So somehow when done properly, and these days a lot of software can do that, is that one nice piece of a scene. Very nice, isn't it? So here one big building and a large building, that's this thing. And definitely this one get enlarged than this one, and even turned around a little bit to make the realistic view. And this statue, something that was shown just once, and then this another objects that's showing. And then here's some, I don't know what it is, but they're bushy and something. So this way of gluing together, piecing together of multiple pictures into one, that is the image stitching, and one very useful and widely used application of computer vision. And then here's another example of not only just a sequence on the horizontal, but also vertical. So if this scenery is too big, then you have the two pictures up and down, up and down, up and down, up and down. This can be automatic, or it can be done by manually by those photographer. Then anyhow, that those things, they definitely has those part being the duplicative unit. This one is the same thing. So duplication here, this part is duplicated and this part is duplicated. Some cases, some pairs have a more overlap, some cases less overlap. So there is no rule or no restriction, and there's a sun showing up. So somehow this 10 pictures of different range, or they merged into one nice big picture. And this is another example of that this piece and this piece. Then you are building a little smaller sized, what doesn't matter. So if there's a certain limitation, you don't want make a large the panoramic, but typical 3 by 4 the aspect ratio type of picture, then you will cut here and cut in here, and some part being overlapping, being just composed properly here. And this is another example of adding these two things together into one. So OpenCV has the very nice function. All you have to do is just call it. So even if you don't understand that what we are covering today in terms of mathematics or those logic, still you can use it, and all is stitching together. So that's why I'm keep showing you the sample of what can be done by stitching. So combining multiple picture of overlapping portion into one. That's the idea. And the panoramic view. So once you do that, then no camera cannot take a picture of all around it. I don't know whether you heard about this, but 360 picture. So when you go to certain amusement park or certain places, then you are sitting here in a big dome, and all around you is those picture showing all around you, and you are part of whole the scene. So you are, it's more like you are inside those picture. So naturally that leads to the virtual reality, augmented reality thing that I'm going to talk about today. So in other words, that the panoramic image teaching is extremely important and essential techniques for VR, the virtual reality, and the other reality that they're coming with the virtual reality. By the way, this is the website, the panoramas of DK. This, I think it's Denmark. This website has a lot of those news and products done with the 360 picture or the teaching algorithms like that. And then the Mars of the NASA recently sent out the spacecraft to Mars to take a picture and get some soil sample and showing those different things. So I recommend you to just click this one. In this mode of recording, I cannot play this, but at least this one, then I opened this the website, and then that's what it looked like. That's that panorama.dk site is a virtual tour. Mostly that tour goes around yourself. So for example, Museum of National History, arts, like that one. So you can, it's as if you are inside there and going around it. You have heard about that thing, right? So even if that you are in different country and the different places, but through the system, through some kind of devices and through the equipment, you can have an experience just like you are part of a whole the system, meaning that you are touring around this the big museum yourself. So it has a lot of samples, like I think it's aerial photographed here, but Everest, the 60 years anniversary, and it's more like you are flying around those the Everest, and then here is an example of USA 360 degrees, and there's some old paintings on a church, so you can look around as if that you are visiting that church in Denmark. That's quite a far place and very difficult to go. So you can have that experience. That is what we're talking about in virtual reality. So it's the nice website that you can visit and enjoy yourself. So image mosaic and then stitching is same kind of same words. So mosaic is piecing together. So to make a mosaic, we need to stitch. So this picture, that picture, that picture, that picture, many pictures, that equals to this new picture. So stitch together several images into seamless. The seamless means that there's no sign of or no trace of that these are the different picture pieced together. That's done so nicely that people they don't see the differences. That kind of the techniques are needed here. That's what the stitching algorithm is working on. So by the way, jumping ahead, there are many the software already on the market. Many of them are free, the open source software. So image composite editor, that's from Microsoft. This one, I think you have to buy it, I think. But auto stitch, and this one is also the proprietary. You pay just a little fee, but Hugging here is a SourceForge, and this is a free, and the Google Virtual Reality. So you can actually get all those. Google is doing a lot of good research on those virtual reality and the AI, of course. So it is well worth visiting. And then Panoramic is another one, so you can go there and they go all the detail. And I don't know whether you have used the software called the GIMP or GIMP. There's a graphic image manipulating program, something like that. It's they almost like a Photoshop, but it got much more features and absolute free. This one, anything that says Star Wars. I used to use this GIMP a lot. It's a little difficult to use, but eventually it works out fine. And then there's a 360 image view. That is another software that you can use for making stitching and panoramic views. And Photosphere viewer is also Photosphere viewer is also the open source software. Then of course the free OpenCV in using the Python as the host language. That one is available, and let me just give you one OpenCV for stitching, and there's the algorithmic kind of algorithmic steps. So there are some words like warping, and then there's the blending and the estimating, the wave correction, that kind of words. So all the algorithm we're talking about today is all given in here, all the programmed. And you can click this their website, and they have a very nice explanation plus a sample program. So I hope that some of you may use this teaching as they make it as your their diploma projects, because that's very useful and very nice looking. So in doing so, that where does the panorama comes from? By motion, isn't it? A camera must move or object must move to be able to take a different picture on the location. So motion is needed. And the warping. What is meant by warp? Warp is at crookeding. I'll explain this one a little later. But the warping means the squeezing or expanding. So as I said, some picture is smaller, then you got to make it large enough so that it matches with the other picture. And some of the cases is that seem to be a better little bit turn around, so that we make a very smoother looking. So that kind of the transformation, matching, and the gluing together is a pretty tough job. So all the days the photographer or artist was spending hours just cutting it, enlarging it, and piecing together. Now you don't like that and throw it away. They use another one. That takes very long hours. Now software can do very fast. Then point-based alignment. So alignment is needed. Remember that we had the feature. The feature then feature comes usually as the point or the corner points or edges or the region, the general open area. So those things that, but based on this understanding of the features, you can do the alignment. So we talked about feature detection and then matching. That was the one subject we were discussing before. And then they finish up those mosaicing. So this is called global alignment. This is all then some more, the minor, but this the algorithms related to this the stitching activities. So the first one, there's a motion model. Motion, of course, is a moving. So there's kinetics. We talked about the motion in previous subjects where there's a motion field and those dynamics of those pixel. So here's a bicyclists, and then because of motion, we got a blur. So motion blur we are talking about. But anyway, that due to the motion, we expect some kind of changes, and that changes can be a bad thing, but at the same time, when used properly, then that's a good thing because by motion you get wider area of coverage, so that's better. Of course, that takes some of the calculation because some portion got crooked or blurred, so you got to compensate it. But otherwise, it is a very useful situation that you can track all the motion and make your image adjusted for that. So motion model, what happens? We take two images with a camera and try to align them. So that's a transformation. In other words, two different pictures, and even if that they are not in same scale, same direction, same location, the camera is somehow changed or object has some changes. Here, especially for the building rarely changes, but camera changes. Either it's shaken or when you're taking picture, you just do sideways like that one. So same location with a different range. This one is a little bit on the left. The building itself, this shows more than this small part. And instead, this one shows a much more of this part. So two pieces together, then we got wider range from here to this much. So that's a good thing, isn't it? But to do that, but this one is first of all crooked. It's turned around just a little bit, and then it has the little closer here, a little larger than this one. So it's closer range and the different perspectives. That is that so-called share. That is that when you see from one corner, then another corner, then same object looks crooked. So that kind of changes must be taken care of by transformation. So what kind of transformation? That's a form change. That's a transformation. As a translation. Translation means just movement from here to here. It's not translating English to Mongolian, Mongolian to Korean, anything like that. It's translation is the position shift. And the rotation, rotation, that's circular motion, and the scale getting larger or smaller, and the shear is seeing from one direction or another direction. So this is square, let me draw this one. You know, and I know, this is not, this is a square, perfect square, isn't it? But this one looks like it's a square, but this doesn't. This is not really a square. Square is like the 90-degree angle. But even if that it is the 90-degree angle of a square on the box, but because we are seeing from that direction that it looks slanted, that kind of thing, that kind of a view is called a shear. Shear, original meaning is that using scissors, you're cutting. So when you're cutting in different direction, then it looks like that. So instead of a straight cutting, you cut a little sideways, that kind of idea maybe. So shear is cutting. Well, sometimes when you are cutting the hair of the sheep for the wool, then it's called shearing sheep or goat. You give that name. Anyway, so it's a geometric changes. Then perspective transformation, that is that when seen different direction, different position, viewpoint changes or view volume, the aperture, remember that we talked about aperture changes, then it may show differently. And then pure plane normal VPN. Again, this one I explained, but I don't think you may not they remember yet already. So that is a projection plane, but that plane may not be straight. Like when you are projecting something to the screen, if that the screen, the fold down screen is in different angle, then you see something is crooked. Actually, even if that I put separately, but share is actually the results of a perspective transformation frequently, but the share itself has all the intentional the transformations. I just gave a geometric, but also it's a perspective transformation. And affine transformation is that combining many steps of transformation into. So they usually was it depends. You can x, y, and the 1. Why this one? There's a reason for that, but there's then A1, B1, C1, the A2, B2, C2, and A3, B3, C3, and then this one become, you multiply this one with that, this one with that, with that, then you have the new X and Y, Z. So the X prime, Y prime, Z prime of the X, Y, Z. 3 dimension, then you got the one, add one more, and this become 4 by 4. So again, this is a long story that actually the translation is a reason that we need one more row in the column. But whatever the case, that this one, well, eventually what it is like is that new X, X prime is all A times X plus by plus c, like that. Actually, I should have written this one. And the y prime is the dx abcd. So actually, a1 b1 can be x plus ey plus f. So you got a multiplicative component and the additive component that actually due to the transformation, translation. So that then this type of thing can have accommodate this the transformation matrix 3 by 3 or 4 by 4 for 3-dimensional. That is that can combine any kind of this transformation, including perspective transformation. So you can combine many. So once you get, then each object has many points to translate or transform. So you just combine all this the operation into one matrix and just give this kind of the calculative the formula, and you do quick calculation. This is something that they are supposed to be covered in computer graphics. So anyway, that's how it goes. So the but great thing about is that when we got the 3 by 3 matrix, a 2-dimensional one, so well, actually it's more like A, B, C, D, E, F, G, H, I, like that one. So 3 by 3, then remember that we could make then some kind of a V1, V2, V3. This is a lambda, and then same V1, V2, V3. Never heard of it? Remember those eigenvalue, eigenvector. So again, beauty of this thing is that any complex operation or the data can be reduced in a small vector, sizes, and A as a vector, and with the help of another constant that you can fully represent the uniqueness of this matrix into one vector. So when any data changes here, then at least the sum of this value will change, and you can make sure that this is different from the other transformation matrix, like that one. So all those the invariant image can be. So once we do, then we can. So what real beauty again is that how do we know that this picture, this site, and this did what is the factor that is not same as before. So for example, we use the first one as model. So this one had this kind of matrix, but we can put that one into eigenvector. Then in here, that we got another matrix, but this the vector is different when you derive it. So force this whole thing transformed so that this matrix is exactly the same, at least in the eigenvector wise. Then they are in same the property, same shape, same scale, same sizes, same rotation. So this invariant is so much useful. So they used extensively in computer vision and image processing. So depending on this is projection idea. So the eye is here, you look, then this is the object, and then this is the projection screen or projection plane, PJ, usually PJP. So so whatever the intersection of this site to point to this, and this intersection over here, so it should be in here, and then this one over here, that one over there, and this one is from here. Once we do that, then our image, of course this is three-dimensional, but this is only 2D, but this one, this image is what we are perceiving. And that again gives you that this one may be the three-dimensional matrix, and this one is a vector of the one-dimensional the shape, so line like that. So it's invariance for the given object. And then again, when this is a screen, so to speak, and then this is where the objects are projected into. If this one moves over, then that shape will be different. But also, if this the projection plane, projection is a projection plane. Why plane? Because we have a two-dimensional surface. This is three-dimensional volume. So this one, if it is slanted, moved around, then we know for sure that this picture or this image will be crooked. So you turn around, or you see the screen is tilted, then you see somehow different shape. That differences or changes of the shape again is called the shear. Okay. So this picture of a plane of a projection, and the picture, and then this is called, this line is called the projector, and this is a station point. And then so from here that you are getting the same logic that this object, 3D object is projected into projection screen or projection plane. Then the plane of projection is what PJP, usually we say projection plane here. And then again the tilting or the shape and the size of this screen, that makes a big difference, isn't it? If this screen is only this small, then you will see only just a portion of them. So there are many factors. That's what we talked about before. So from here, there's the human observer or viewer is here, and this can see here, 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 here. So projection plane is moving around, so to speak. So the projection plane is moving around, and you're taking pictures, and you can do the stitching. So while doing so, then you have this the projection operation and this change operation that is given. So there's a motion detecting, and that the changes can be recorded into matrix. and then we get the invariant vector and the value, and we can adjust based on this the invariant, this fixed form or standard form. So here many parameters are needed. So light source, this is something we already talked about before, but so the reference point, and this is where the origin is. Again, this is something that I actually I kind of imported from my handout in computer graphics, the course I taught. Then there's one thing about this. There's like a view up factor. The screen may be on the right side, but you turn around, then the picture will look crooked or turned around. So that's a view up vector. And the view plane normal. This is something I wanted to talk about, but again, it's a little hard. So how do we know that the screen is tilted or standing? How do we know? That the better way is that let's have one vector that is perpendicular to this plane. That's a view. This is a projection plane. So projection plane, and there's a vector that's the perpendicular. So when you tilt it, then this vector will change. So this one is called the normal vector. So view plane normal means that what kind of vector it is. So this one determines, this view plane on view Pn determines the orientation of a projection plane, and therefore what kind of a crookedness or sharing effect do we expect out of this setting. That's the idea. Then the motion field that we talked about the other day, in previous the lesson, that the depth is important. Z is the distance from observer to the objects, and then this is a speed, and from the original location to the next location, how far they are going. So the length of motion vector is inversely proportional to the depth of Z. In other words, that this one, the farther away it is, a Z value or the depth value or distance value is the larger, the amount of change is smaller. So length of motion vector is smaller. So all the vector of this motion is farther away from us. And then when the VZ, that is the initial one, at the Z, is a non-zero. Every motion vector point toward the vanishing point. So in other words, that when it is changing, it goes toward to a certain location of farther away. So motion, in a sense, is not reaching them, not necessarily, but moving away or moving from that far places. So those are in the perspective projection, where is the ending point? Because the smaller it goes when it goes farther away, the far away. So remember the railroad track looks even if they're all same length, but it looks narrow, and at the end we see just a dot. They are together. So that's called the vanishing point or merging point. So the idea is that anything that goes farther away, that is smaller. In fact, there is a name for that. Let me give you that one. That's foreshortening. That is that for means far. Far things get shorter. Makes sense, isn't it? So any object that's way away from us, it looks very small, tiny, and close to you is big. So if you have a pencil and go near the eye, then it looks whole. It's bigger than any tree in the world, but it goes farther away, then get very lean, small stick. Then there's another issue about the warping. So warp. The meaning of warp is that this crookeding. So squeezing. So actually this warping is used in the space odyssey or the astronomy when you are traveling over the universe and going to another planet, another galaxy, like that one, then whole universe looks warped or this crooked. It's not straight line. It goes a certain the crookedness. So warping usually is it. But what warping in this sense of stitching is that you just squeeze it. So it's much like this way. Here's the one picture that its length is this much. But same thing in another picture is this one. Why? Because this is farther away. The foreshortening, the farther away thing, even if it's the same length, when that goes away, then that looks shorter. Then somehow we got to match this guy up. So we are somehow squeezing down and like that. So like that and then like that. So if we have those things going up and down, the squeezing, then it'll match up the sizes, isn't it? So that's a warping, is the way crookeding, squeezing, that you make a same size, or stretching and expanding, you fit to a larger scale. So here's a smaller one. It should be stretched out and stretched out. So that stretching action is a warping by squeezing, twisting. So in here, by image filtering, that this kind of a curve can be shorter, in a way the less the deep, so it's a little the smaller and a little farther up. So that is one of the those warping. So some function, warping function, it changes the same data but it's smaller. So suppose the other picture we want to stitch with, that happens to be bigger, I mean the smaller, then you will squeeze this the size into smaller size so they can fit. Then this one is squeezed, they are shaped like that. Then you want to make it squeezed, smaller size, and farther away the center into. So delayed into. So this is translation. This is scaling. So that operation image can be switched up. So warping is just nothing but changing its shape by squeezing or stretching. So in here, that then not only the size itself, but it can change the image intensity. So here's the certain color. Then you want to make it brighter, much brighter, by adding those pixel intensity value. Then it'll go much like that one. It can be consistently, uniformly, or it can be just say, okay, I'll just make this part a little brighter, but the rest of them is the same, like that one. Then also that the domain-wise, that it can be the aspect ratio. I said, suppose this is 3:4, then let's make it as 2:5, like that. So you are squeezing it. You are doing this one all the time. When suppose even in PowerPoint you have a certain picture, and then you want to the paste in here, but you can stretch it out, squeeze it, or you can make it the squeezed on the vertical size. So you can have. Then it's changing as a translation, that rotation, and aspect ratio wise is squeezing differently. And I'll find this a multiple squeezing, rotation, sizing differently, and the perspectively farther away. And the cylindrical, that is that it translate, or it make a calculation based on some kind of a circular form, because of the older cylindrical form, so that the many pictures, they are not just a flat, but it may be. So we expect is, so far stitching is that every sign, every scene, the pictures are stitched in linearly, but Why not? That we are seeing one place and we are looking around. So 360-degree picture or movie is actually, you got to make this one, way rotated. It's much like the inside kind of a dome. So you got to translate such a way that it's squeezing a little bit toward to you than outside. So the cylindrical, the transformation is also very important. It will be covered later. So there's some the equation like the translation wise, we need the x, y2, so y prime equals y plus tx, then ty, like that. So this is x and y be done separately, and the rotation. So we have a rotation, this cosine theta, sine theta, like that one, and then the similarity wise that if it is the same value, then everything is x new. The value is that old value plus some addition, like a fine transformation with some constants and some scale factors. That way that we have a same picture or same scale or same shape, but nevertheless different transformation. So this is simpler one, ax plus t. So affine is nothing but that multiplier and adder, or those additive components. So any function like y equals ax plus b, this is affine. It's this multiply, this a times b, isn't it? So multiply and adding this one, that together, that by combining, that's affine transformation. And luckily that this we have a x, y, 1, and this, and then become the x prime, y prime, and 1, like that. In this case, that these values, those are the values, are all translatable by x prime equals, and then like that. Also x times ax plus b, the b, and then y prime is y times b, a y plus this bx here, like that one. So multiplier, this is constant, and adder, that's also constant. That's the affine transformation. And similarity is that our affine transformation with some scaling factors. The perspective one is almost the same, but there's a certain h value, the homogeneous the coordinate system. Again, this one is all the graphics terms. So homogeneous means that every transformation has the same format. Like I said, the 3x3 and 4x4 if it is three-dimensional objects. So everything is on homogeneous coordinate. That's what it means. Again, I'm just jumping around with the computer graphics subjects, so it doesn't make much sense, but just please bear with me. And in a way, they will be already included in one. So closed nested group is within this one, two, the dimensional, the coordinate system that is transform, the translation, rotation, scaling all work together. Again, the image warping is that they are somehow changing. So here's the coordinate system of this origin and x-axis and y-axis goes like that. So this function, then we are changing. So new system again has a difference. So every point is somehow in a way rotated to a certain amount. It's the same picture and the rotated amount. But in here again, scaling is somehow different factor. Then you have to combine the translation, the rotation and scaling together. Then in here, that each pixel goes to corresponding location of hx in gx. So in here, that this hx is the location on a different location. So the original function original pixel location. The function is they say that where the value goes here, that value must change to this location of gx. That's expected changes. So what if a pixel lands between those two pixels? So we got some point that this one goes to here. That's what we are talking about. And this one goes to there. And then this one goes to there. So in doing so, sometimes the calculation is such a way that our pixel that calculated is somewhere that between these two points in here. What we do, you got to do interpolating. So from one point that goes over here, then what happens to the rest of them? So add a contribution to several pixels and normalize it. So calculate the many of them. It's like a neighbor and like a convolution. So you can just calculate new value over here, from here, and that change is being now that later adjusted back into which one belongs to which, like that. So sometimes, remember that we talked about the reading the license plate from moving car. There's a motion blurs, so you could read that the license plate, but now you are reading it. That is that we are reversing the situation. So somehow it's a rotation or some moving. Actually, a car is moving this direction. Then one point here will move to that point, and this point will go over here. But as it goes so farther away from us, then it may become smaller. So we have to make it narrower location. That kind of a translation, the transformation is all needed. So we got to this is what we observe as a blurred image because of motion. Then we are moving the pixel back and then move this pixel back here. Then we got more the stable picture. So this point goes over here. So very much like this little picture will move over here, and you can resample it. So there is another, what if calculation needs a further refinement, then do the sampling again and do different picture location. Then when this points and that point and this point's missing, you have to interpolate it. You know the interpolate. So remember that we talked about where we could have this just a partial line in here, and then there's the gap, and then another line. Then we can search around and then connect that one. So eventually we make a complete line. We called that one relaxation. So we could have done as the interpolation. So it is searching from here, this much it has a line, but it doesn't have it, then it searches around it. So from starting straight and go around it, and it searches to a certain range and go to the other location and see how it goes. So it's much like you're feeling the blind man feels when they walk around, and then you feel here, like that one. So the line goes around it. So many iterations later, you got this connection being done. That's interpolation. So that doesn't exist. The pixel that can be connected or found by searching and connecting to. So it can be nearest neighbor or by linearly go, or it can be cubic, searching around. And then there's a sign, the synchronization, the operation. So the prevent jag and well, that's the not that important, but anyhow, that you just find right type of the interpolation. There are many techniques of the interpolation. So motion model-wise, there are many. So there is one portion, this part, and that part translating, and then this is all fine, so multiple. So in this case, that all you need is that how much, say, suppose this is moving to this one, they too much. Actually, this is a little confusing, but this piece to this piece. Then our window, this corner is changing to here, and then this corner is changing to here, this corner changing to here, this changing to corner. But they are all same amounts. So what do we have to know? How much x we are changing and how much y we are changing. That is all we need. So the new value of x prime, new value is old x plus delta x. And the new y is old y plus delta y. That's all there is. But if it's a fine transformation, then we got x prime is ax plus by plus c. Remember that? So it has all x and the y value be combined. Like a rotation, then what was y is important. So you got to have that and some constant. The y prime will be the dx plus ey plus f. So 1, 2, 3, 6 of them, 6 unknowns in a affine transformation. Then if it's a perspective, then we need to know the location of the xy of those view and view plane normal, and then the view volume and the view up factor and the view plane normal. Many of those factors that actually adds up to all 8. And the when you are doing 3D rotation, then you need an angle. So 3-dimensional rotation, then how much you are rotating on x, how much on the y, and how much on the z. So you need the angle. So theta and the phi and the phi, the psi or something. So you need the angle of how much you do on x-axis, how much you do on the y-axis, how much you do z-axis. So you need the 3 unknowns like that. So give that parameter, then we will make those kind of changes. So here's many kind of a transformation possible by motion. So motion is very complex because it is one car here moving and changing. So it may not just straight in the way we watch, but it may be going that direction farther away or turn around. And sometimes that it come to me, closer to me, then it makes it bigger, but always smaller like that. So plane perspective mosaic goes that 8-parameter normalization of all those parameters we have seen in previous in several slides back. So the using those things that you generalize, and then you got reverse the calculation. So it's a lot of work in here. So image warping with homographies, that image plane in front, it can be, or it can be in the below, or it can be up like that. So there are many different ways. And then once we have done transformation and make as much of the adjusting done, then we'll use the mosaic of the image. So we already saw that there are these pictures can be all combined into one. And this picture has like a ball player. In the field, it looks like somebody playing tennis. So there, then so tennis or whatever. So this one is very small pieces and doesn't give much of idea, but this looks much better, isn't it? And then this is a little bit panoramic. So it can be straight, or typically the stadium or those playgrounds are round, so that the players in the center and the people seeing around it, there's nothing like a straight all the time. So we may need some cylindrical. This is cylinder, so cylindrical transformation. So correspondence, there are a few of these researches, and where do you look? So the surrounding is a 360-degree, and where do you look? So here or there, like that. So projection cylinder, over here there's a cylinder of watching. So when talking about the panoramas, then we usually do it in the cylindrical manner. There's a circular shape here. So this is very complex objects, like those the virtual reality, the virtual tour. So you have one layer, another layer, but all around all around this cylindrical form that gives the feeling of you are inside the building or in the field. So it is the cylindrical, the panoramas in here, that each one with the different angles. The picture was taken with the different angles, and that combined together, then we see that this one in a cylinder, and we are inside that cylinder. So yeah, so align the image over each other and blend the image together, then somehow that we feel like we are standing inside those picture. Usually, so far, most of pictures was that we are outside of that picture. Now that we are inside that picture, that's the great thing about the virtual reality thing. So image stitching orders goes as take pictures on the tripod or handheld, and warp image to the cylindrical, the spherical or cylindrical coordinates, and extract the features of which points and the edges and the regions, and align neighboring pairs using RANSAC. Remember this random sampling, consensus, random sample consensus. Yes, so using that neighboring pair, they say which one is corresponding. Yeah, we talked about the RANSAC quite a bit, but it's a little hard to understand. But they just know the name only, so it is useful in understanding the kind of dynamics of a picture, how they are changing. They write a list of neighboring translation and correct the any kind of a drifting changes, or this one is error due to your hand is shaking or some other factors, and read in warp image and blend it. And the warped means that all standard sizes, and crop the result and import into a viewer. So the easy to say, but it's a lot of work. So in here, matching features that we want to match this picture with that. Then we say, aha, this line is that one. So you got to detect the edge. And then when you are detecting edge, you got to have identified many edges. And then here one corresponds. So you are doing RANSAC, random sample, and the consensus, that's agreement. So you sample here, and which one, this one hits that. Yeah, this sample is same because of this dynamics, and this dynamics are same. Then there's another one from here to here. There's a different texture that's the same, and this one corner of the window and that corner of window is same matching. So you keep looking at those different matches. So matches. Unfortunately, that this red one is a bad match. In other words, that this one is the same as that. So oops, we thought that's the match. This one, we thought that's a match. So there is a chance of a mistaking or the mismatches. So bad matches, then what we do? So in the case that select one match and count which one, how many of them. So we have a match from here to here, and then how many of nearby pixels within here are matching. So with here. So suppose that I got a 1 point and the size of like a 20 pixel radius or square, and over there the 20 pixel square, and see if there's any correspondence. So if it is the bad match, wrong match, then you will find out that there are so much of discrepancies. So suppose that this block and then this block has been matched by wrong match, then you will soon see that there's other factors like those railing and some other decoration on the windows. They are different. So you say, oh no, that's not matching. So random sampler keep working this and that. So say, aha, this one and that one has so much discrepancies, so we are not going to match that into like that one. So some of them are bad matches. The red one is this one. When you keep going on, then in here that when it goes back here like this sizes, then there's nothing, or they are different building the structure. On the other hand, in here, this is another window and another the column of the building. So this one is not matched. So red one is a wrong match, and then green one is a good match, and the blue one is something we are checking like that. So you are keep adjusting. So you are we are checking whether this is the right one. Oh, that's a blue. Remember, that's something in question. So the other ones are all good match. Then this cannot be a good match because there are other members that with a shorter length of the vector that is they're matching, but in here this is way too long, so it knows that it is wrong one. So find what is average. So average size, so the length from here to here, here to here, or kind of uniform, but this is too long. This is too long. So average is about this much of those things. So it should be longer than this guy because of the long member. Still that what is nearest the matches. So the green ones are much closer to here, and the red one is farther away. That's what again says ransack. Randomly you sample, and then say consensus, make a decision based on. Then assembling panorama, the stitching pair together, blend, then crop it. So you match it up and down, and then you, as needed, you got to cut it. So down there, that how much the overlapping and the size may be different from one match to the other, but as long as there's a feature detection, again, the key of those the matching is a feature detection, and then you will decide, or you will make a sense about where you stop those matching area. Then there are cases that it can be up and down, so that can be error can be accumulating over. So what you do is that you standardize those distances. There are many the techniques, but here go up and down, up and down, up and down. So what you can do is that in a way that translate everything into this location, that much of a same shape, and the same location, and see how much it can they work together. So that matching takes some work, so it takes some time to do the full calculation. But anyway, 360 is spherical or 360 video of a panorama. So there are two types. I mean, that is both of them 360 degrees and full views around it. So these days is the common technique, and you go to some exhibit or some museum or some amusement park, you will see that a lot of those movies made. So you watch it and it goes around. Sometimes the picture moves, or sometimes you move yourself and it looks like you are inside there. Actually, it's better that the picture stays there with their own animation, and the people just look around and get those feeling that you are inside of something. This is the this is one example of the Utah video. Then, so that one, if you look at those the panorama.dk site, then you will see that. Or you go to YouTube, then you will find that. I think I left that one somewhere. Then you have this 360 degree the panoramic the view of those pictures like what we had, and sometimes you need to more realistic. To make it more realistic than not just a flat display, but some kind of texture. This looks like some painting done or some wallpaper being given, and sometimes you put some decoration. So you need the overall global, the alignments overall view, and you give the adjustment to each other. So 3D rotation model and the direct alignment and the overlapping part, and then cutting as needed, and then for the match matching, you do the random sample consensus. Then you do blending images, so you got to make those images together. So when they are together, then sometimes color may change, shade may be changing. So you correct or you adjust that into those value. And then here, for example, that those height is somewhat different, then you will you will make that on straight by this same scale, some scale like that, and add up, then you will be giving the much smoother and the uniform shapes. And the image can be feathered is more like same shape being repeated over. That's feathering. So it can give some kind of a combination of this is one picture and this is one picture you combine together and make more varieties. So you can by image stitching that you can they make the background more interesting. And here, what they in that feathering, what it is, you hide the half of this image and the left half of the image, and anything dark will be all overlapped together and they removed and then combined together. That way, that you got those things combined, and the connection point is very smooth because of those darkness that goes somehow not just a straight line, but some kind of random the waving here. So it will become just to look the natural. And here the left and right being overlapping, so different window sizes can give the clarity. So there are many of those the algorithms, and they, depending on window sizes, some result may be good, some result may be a little bit awkward, not very nice. Then there is a blending, so you are adding these two pictures together by combining it into. So you have a larger scale and a smaller scale, and in the pyramid case, that a certain portion gets part of the apple, and a certain portion gets part of those orange, and combine it. The blending is combining together. So Laplacian is actually more of a Gaussian. You just spread and get the random samples. So left pyramid, right pyramid, and blended pyramid like that also from larger scale, smaller scale works. So this is very time-consuming calculation, but the result may be okay. So in here there's steps, but we are not going to use this one. So I'm just indicating that Laplacian, the blending is needed. That is combining many the images together. That's when you are stitching two images together, then you have to somehow blend it so that it looks very natural. Remember that what is called seamless. So there shouldn't be any kind of a sign of a straight line that is glued together, but they look very natural. That is the idea about this, how to make those things. So just to think about is that you have one picture and randomly they make a borderline into the darkness and so this is a picture saved as it is, and this is you darken it. But those borderline you generate as random. Same pattern will be translated over here. Then all the left of those translated borderline will be the darken out, and then those borderlines supposed to be exactly the same. So you fit into, then you have a bright side on the left and bright side on the right of a different picture, and the two merging gets a very natural looking. That's what the Laplacian is doing. So, and the Poisson is that the Poisson is a random sampling. So here the image editing wise that you can use the Poisson distribution. Poisson is more of a randomized distribution of this picture that when they sampled randomly and with the averaging into those fixed sizes, then eventually then you got the clarity of this one. So you just pick those objects, those ranges over here, combine here, blending here, and then you do image editing of adjusting, gluing, and the unifying those the characteristics, then you come up with a very natural looking shape. That's a good thing. So this one more time, this one we had before. So by the way, that this crease teacher is the one OpenCV command, and then stitch images. So you have as many images as possible, and this is output panoramic, panoramic, the panoramic. So this one, this panoramic, the shape, what it has is optionally having this one means is that when you're stitching, you have already some glued together, then you can add more, you can stitch more. That's the idea. So here's the logic. There's input images and the resizing and the feature detection here, and the matches here, and then select those images as the properly usable in the final stitched images, and then refine camera the parameters. That's the view parameters, and the wave the corrections. Sometimes that the color or those intensity may be different, so you just adjust that one, and then you just save the data as needed. Then see you're working. There's adjusting, sticking, adjusting those images so that they are in the same same sizes and same shape, and the blending image here. So what we talked about markings, blending is all belong here. But you don't have to worry about that, how do the blending, because it is all calculated by this one command. That's the beauty of those they're using somebody's their software. So OpenCV has this wonderful features all calculated into. So if you want to play with that one and want to work on this image stitching operation, then you can go to this website. Then this one gives OpenCV and Python for image stitching. So the output, this one we already saw, so I'll just pass it. Just the last few, maybe 10 minutes, I'm going to talk about. You heard about VL, AL, ML, XL, SL. Wow, I heard about VL. Well, I heard barely AR, but is there many? Yes, there is. Virtual reality, we know that. So computer aided is the simulation. So virtual reality is 100%. It is fake, meaning that everything is inside the computer. By the way, when we're talking about the industrial revolution, first generation, second generation, third generation, and now we are talking about fourth generation industrial revolution. This one's steam engine, electricity. This one is computer and internet. This one, what they call cyber physical. What does that mean is that all the cyber, that whatever inside the computer will be actually merging with the physical world. Virtual reality is still more of just the cyber level. So what you see is that they feel as if it is some new the location, new pictures like that. But augmented reality is that the reality is that adding virtual reality component to reality. So for example, that I have in my desk that I want to have the data about the weather. Then the data, the weather is showing on my desk. Sometimes a three-dimensional model of those universe or molecule that I'm researching on. That is being shown. So in the real situation, you see some kind of application or some kind of images and some kind of motions showing. So augmented reality is that adding virtual reality to reality. So physical part might be added. Then mixed reality is that virtual reality and AR and the other sensory interaction. So in here, all you see here in AR is images. But what if that there's a sound coming up and you can have a smell and you can even taste it or you can touch it like that one. So it is much like your experience with working with certain products down there. Like you are going to shopping, you are not here. Like Amazon, you order some objects, there's some products, but this one, the mixed reality is where you go to with a goggle, then the virtual reality and the actually augmentation, and then you go around and you can touch it and oh yeah, here's a cloth and it's a very nice the feeling, the fabric is good, color looks good, and smells good. You go to those cosmetic area and you smell it and you just check on it. So all those kind of senses are added to by some other devices. That is called the mixed reality. So it's a halfway reality, halfway of the cyber. That's the idea. Of course, this is in development, and we haven't quite a bit came to the reality yet. Then extended reality is that that's just a term given. So ER, or actually called XR. XR is that the term talking about all those virtual reality, augmented reality, and the mixed reality together. So one more time, virtual reality is 100% computer generated the world that you see, you feel or you perceive visually. Then augmented is that you have some real world situation, but there is something added to you, to that location, and something images showing up. So like these days that I'm going to talk about that one later, but those Facebook become Meta, so metaverse indicates that you move around and you see just the screen just showing up and give you some data, and the sometimes on the desk part there's some kind of model showing. I think I got a picture in the next page, so I'll talk about that one to understand the augmented and mixed one better. But mixed one and augmented, the difference is that mixed reality has all the other sensors. The augmented is just a visual, the display, that's mostly, but you cannot touch, you don't feel anything. But the mixed reality, that all the sensory, the perception will be given, and the extended reality is just that, the meaning. Substitutional reality is the experience of MR, the mixed reality, without the special hardware. In other words, to enjoy, so to speak, of this virtual reality and augmented reality, those kind of thing, you need a special goggle and you got to have all those equipment. But if the whole world is around you and everything you can touch, feel, but that happens to be the generated by computer system, and you can even touch that one and get a feeling you can get. That's wonderful. Of course, that substitutional reality is in development. It may take another 30 years before we actually fully enjoy it, or it may never come. But anyway, that is the goal people are working on. So this is an example of the augmented reality. So with this goggle on, and on here that I want to have this is a mechanical, the engineering students. Then you can say, oh yeah, this one. So what if that I turn around, so I gesture to turn, then the display shows that underneath of that, I want to cut it off and see the different inside of those, the cylinder, what is there. Then you can do that, but it shows it by your motion, your command, or you press on the key, then you can have those detailed the shape of this the gear. And then sometimes that there is another picture like when the parachuting, then indicates that how those things are changing differently. So actually that time that all the shakes and the feeling can be existing. So that kind of thing is the augmented or mixed reality. And the metaverse, of course, is that new Facebook here. So the Facebook changed it to Meta this year, so that is a Meta here. And then it's a person online 3D environment and using virtual reality and AR so far. So you can virtually talk to others. Virtual reality chat is that you can talk. They not only just these days it's just a message sending and you reading in a text or some pictures or video you look. But now with this and with the goggle on, that you can actually talk and you just get as if that is you are looking face to face and with a certain the room setting like that one, or some when you're studying the universe, so the astronomy, then you can see those stars, the skies you can see. And then here's all those and the Second Life is a game. I haven't used played this game, so I don't know how it is, but it's a very realistic looking. And then here's the actual setting. So it's a metaverse is the virtual reality. So meta is the common or top level what it means. So you can have this kind of a scene and arrangements, just like as if that you are part of this it's a garden or this location with this the fictitious. So these are not real people, but looks like a real people, and you talk to them and work with them. So anyway, piecing multiple images to one image takes a good alignment, transformation, warping, and the matching feature detection. The matching algorithms for matching feature detection and matching algorithm is used, and the RANSAC is very useful. And even for smoother stitching, use panoramic Gaussian and the Poisson image. And image stitching and mosaicing is more important in using 360 video, AR, VR, metaverse. That's an example of this application. So stitching gets very much important for new the age of computer developments. Okay, this hour and a half, so I'll stop in here, and thanks for listening. That's all.